In this work, we present CLHOP, a method for 3D pose and shape estimation of horses that leverages audio information to improve reconstruction and resolve visual ambiguities. Horses produce sounds as their hooves come in contact with the ground. This sound, the rhythm of it, tells us how they move. Our goal is to recover the 3D articulated motion of horses from monocular videos. However, the recovery of full 3D pose and shape from monocular visual information is difficult, especially under occlusion. Our idea is to use sound to complement visual information to improve the accuracy and robustness of the reconstruction. We propose two fusion strategies to integrate audio and visual features in different ways for estimating 3D pose. These two fusion frameworks are based on the Share Backbone module, image-only network, which adapts the CLHOP architecture, which is originally designed for single image, to handle video sequences. The image-only network consists of an image encoder with ResNet backbone and a temporal encoder to extract visual features from video clips. Shape is predicted from visual features and supervised with silhouettes. For pose estimation, the global rotation and the pose parameters are estimated from visual features with a fully connected layer and a regression module, respectively. Regarding the fusion models, we first compute audio features from spectrogram images aligned with the video frames. And in early fusion, visual and audio features are concatenated before the pose prediction module. In model fusion, the visual and audio features are processed separately through the same module to predict the 3D motion. We demonstrate our method on two datasets. An indoor mocap treadmill dataset with 7 subjects, trotting on a treadmill, and an in-the-wild outdoor dataset with 4 subjects performing diverse motions, walking, trotting, and cantering in different directions. On the treadmill dataset, we extract silhouette from OSVOs and 2D key points from projecting mocap markers and deep lab cut. We randomly select 3 horses in dark colors for training, and leaving the other 3 horses in dark colors for test data 1 and the white horse for test data 2. We create a simulated experiment. Specifically, we add synthetic occlusions to the test data and evaluate the network performance. We report the mean per 3D joint position error after rigid alignment with Procrustes analysis. We also test the image-only network with color jittering as data augmentation. On test data 1, we can observe that our networks have similar performance, and fusion networks are slightly better than the network with data augmentation. When training and testing data are visually similar, the visual information suffices. On test data 2, we can see that model fusion network has the best performance. This indicates the audio is an effective way to improve the robustness of the regression when the test set is visually different from the training set. In the synthetic occluder experiments, the simulated occluder covers a large area of body parts of the horse. We observe that such extreme occlusions impact all networks' performance. However, the model fusion network outperforms all others, which confirms its robustness. Here are the results for test data 1 on the treadmill dataset. We see that image-only, early fusion, and model fusion networks perform similarly. Here are the results for test data 2 on the treadmill dataset where the visual appearance is very different in training. We observe that the model fusion network predicts better poses. This indicates that audio can be used to mitigate the effects of out-of-distribution appearance during test time. On the outdoor dataset, we extract silhouette from Detectron 2 and 2D key points from VitPose Plus. We have 2 training strategies, a per-horse basis training and an inter-horse training on the outdoor dataset, to address the challenge of varied outdoor lighting and the horse's unconstrained movements in an outdoor environment. We now show some results in the per-horse basis training. Here, when the whole horse is visible, all the frameworks generate similar results. But when only using 2D supervision, 3D reconstruction is ambiguous in the depth direction. Here we see that the audio-based networks can generate better 3D reconstruction when the horse body is orthogonal to the camera. Audio-based networks are also more robust in case of ambient occlusion. Notice how the output changes when the hind legs are occluded by the human. We show another results when the head of the horse is occluded. The image-only network produces an unnatural head pose that points to the right side, while the fusion networks predict more natural neck poses. We now show results for different horses and motions. In the inter-horse training, we train on the black and brown horses and leaving the other dark-colored horse for test data 1 and the white horse for test data 2. We also add synthetic occlusions to the test data and evaluate the network performance. We evaluate the network performance in 2D using IOU on full image frame and PCK based on the pseudo ground truth. With the original data, we observe that all networks perform similarly on test data 1. The performance on test data 2 increases when the networks are trained with color jitter, which shows that incorporating data augmentation during training helps to reduce the domain gap between training and testing data. Regardless of whether combined with data augmentation, the model fusion network provides the best performance. Our results consistently show that the model fusion network is more robust to noisy visual cues from corrupted test data. In conclusion, we have collected an outdoor dataset with different horses performing different motions on a gravel surface. We propose 2 novel frameworks to combine audio and video for 3D horse reconstruction. We have shown that using audio enhances the robustness of regression networks for 3D pose estimation from monocular videos. Thank you for watching.